Okay, so you will need improper integrals other than solving interesting puzzle-like volume and surface area problems. You will need this next semester for infinite sums. When you have an infinite sum, the main question is, does it add up to something finite? Okay, there are several tests for this, but most of the tests compare your infinite sums to sums of the form 1 over n, 1 over n squared, 1 over n cubed. You add the reciprocals of the kth powers of integers from 1 to infinity. Does it add up to a finite sum or not? Okay, so the only way to show whether they converge or diverge is in general using an integral test. You compare this sum with the area under an improper integral. So this is going to be the main purpose of doing improper integrals. But as I said, we can look at several interesting puzzles. You can construct a container, an infinite container, which doesn't contain enough paint to paint its surface area. Okay, so that's a puzzle, but improper integrals will give it. So what's an improper integral? But before that, what's a proper integral? A proper integral, to begin with, f is continuous on a closed and bounded interval. So this is closed and bounded interval. Okay, then consider integral from a to b f of x dx. So this is a proper integral. So for our purposes, f is continuous on AB. If you want to be absolutely correct, we want f to be integrable. For f to be, one of the conditions for f to be integrable is that f is bounded on this interval. So in fact, here we need bounded. Okay, so these are the conditions. F is bounded on the interval. The interval is closed and bounded. The interval is finite. The endpoints are there. Okay, and everywhere the function takes a nice value. Moreover, it is integrable. But generally, we work with continuous functions. So we start with a continuous function. Now, what if the interval is infinite or the function becomes infinite? Okay, so that makes the integral improper. Okay, an integral is improper if some of these conditions are violated. Okay, so basically we have the interval bounded. So you integrate, say, from 0 to infinity as we did over there. Okay, so that's an improper integral. Okay. And the function is unbounded on the interval. Okay, so the interval therefore must miss some points. Okay, if the function becomes infinite at that point, it means you have zero division there, so you don't have that point in the domain. Okay, so generally we put these things at the end. Okay, so generally we take these missing points as endpoints. Okay, so this is the idea. So we say, let us make this in a nice, tidy manner. Let us classify these things. So our function will be nice, say, continuous on an interval from, say, 0 to infinity, or we will have f continuous on an interval of this type, but either this endpoint is missing or this endpoint is missing. So, okay, let's see. So basic improper integrals. Okay. So the first one is, we don't want to number these things, just know this. F is continuous on an interval of this form, a infinity. Okay. We define integral from a to infinity f of x dx as limit. So let me see what we are using here. Okan Hoca uses C, but I always in my life use R, so I'll write R here. From a to R f of x dx. Okay, so observe that this is a proper integral. This is a proper integral. F is continuous on a R. F is continuous on a closed and bounded interval. So this integral is defined, and when you evaluate this integral, you get an expression in terms of R. This is a number, okay, but this is R, a parameter. And then you take the limit as R goes to infinite, okay? Sometimes the limit exists, sometimes it doesn't, okay? But this is how we define it. If this limit does not exist, we will say that this integral does not exist. But I'll say this, I'll make that terminology clear in a minute. So let's see. Sometimes the infinity is on the other side, so f is continuous on minus infinite a. Okay, then define integral minus infinite to a f of x dx is limit r goes to minus infinity r to a f of x dx. Okay, so again, this is a proper integral. F is continuous on r to a, closed interval. Okay, you calculate this, you get an expression in terms of r, and then you check if the limit exists or not. If the limit exists, that's this number. If the limit doesn't exist, then this doesn't exist. Now let us come to the second part. The function is unbounded. But sometimes the function will be bounded, but we don't know its value at the endpoint. So that case is also covered here. F is continuous on a, b, okay, on the half-open interval. We don't know what happens at b, or we know that at b, f becomes infinite, okay? In this case, again, define integral from a to b, f of x dx as limit r goes to b from below. Okay, so you have to take this limit of a to r f of x dx. Okay, so this is our picture. This is x, this is a, this is b. Okay, we don't know. Probably the function, the graph of the function is like this. It goes to infinity here. So you choose an r in between. You find the integral of the function on this interval, and then you send r to b. It makes sense in our example when r goes to b from below. So you just you check the sign here. Okay, you don't want the other. You don't want r to go be from above, because you see then you are crossing this point where the function is not defined. And in fact, we don't even know if the function is defined here or not. And similarly, the other way around, f is continuous on a, b. So we define this integral a to b f of x dx is limit r goes to a from above, r b f of x dx. Okay, so in this picture is almost the same. A. Okay, this time you choose r here. You calculate the integral of the function on this interval. Okay, so that exists. And then you send r to a from above. Our terminology is as follows. If the limit exists, then we say the integral exists or it converges. Okay, so these things are called improper integrals. Okay, so these things on the left-hand side, they are called improper integrals. Okay, so these are called improper integrals. If the limit exists, we say the integral exists or it converges. Okay, so next semester you'll use these terminologies for infinite sums. If the limit does not exist, we say the improper integral does not exist, or we say it diverges. Okay, so here observe that, for example, in this case, suppose f is continuous on this interval also at the end point. Okay, suppose f is continuous on the closed interval ab. If you calculate this, you'll find out that you just get, then this is a proper integral. Okay, but if you calculate this limit, you'll obtain again this limit. So improper integrals are not creating something new if the function is nice. If the function is continuous on a closed and bounded interval, then if you treat it as an improper integral at either endpoint, you'll get the same value as the proper integral gives. Okay, so these things are generally used when f has a vertical asymptote at the endpoints. Okay, so f becomes infinite, and if you check, still there is finite area under the curve. Sometimes there is, sometimes there is not. And the other one is obvious. Okay, so this thing goes to infinity. The interval goes to infinity. If the function is going to 0, then there is a chance that there is finite area under it. Okay, so you check if the limit, if there is finite area under the curve. Okay, so let's see. Okay, let's do some examples. Now, the reason why we use this exist and convergence stuff is sometimes we can explicitly calculate the value of this. Okay, so the theory says that find the limit, that's the value. But we know that most of the time we cannot find the limit, because you see, in order to find this limit, you must know an explicit antiderivative for this so that you evaluate this and you know an expression here. Okay, by experience, we know that's not possible all the time. So instead, we try to find other methods which guarantees us that this limit exists, but we don't know what the limit is. Once you know that number exists, now you can attempt to find numerical approximations to that. Okay, then it makes sense. If there is no such number, and if you try to find numerical approximations to that, well, possibly you'll find some numerical approximations, but they don't have a meaning. Okay, so the examples we do are first the nice examples where we can explicitly find the value. And then we will look at techniques of checking whether the integral converges or not without actually finding out what the value of the improper integral is. Okay, so first easy examples. Okay, so the first example is from 0 to infinity e to the minus x dx. So what we are doing here, if you look at the picture, now I'll exaggerate, of course. If you draw, if this is 1, this is 1, this thing goes like this, and there's no way you can plot this in real life, okay? Because e to the minus x is very, very small. But we exaggerate, we say that suppose this is the graph, okay? So it's never like this. So this is y, this is x, this is y equals e to the minus x. So from 0 to infinity, we first take an r, we calculate the area under this, and then after we find that area in terms of r, in that expression, we send r to infinity to check if there is finite area under this infinite strip. Okay, but here, okay, let me do this like this. R goes to infinity from 0 to r, e to the minus x dx. Okay, so now this thing is something I can handle. I know an antiderivative for e to the minus x, which is minus e to the minus x. Okay, so I carry this limit here. So this one is minus e to the minus x from x equals 0 to x equals r. So I evaluate this thing. I'm again carrying this limit sign with me. R goes to infinite. So this is 1 minus 1 over r, right? E to the r. 1 minus e to the r. Okay? So now I take limit as r goes to infinite. You see this expression is nice. I can take the limit. This is 1. So the area under this is 1. So if you plot this properly, you will see something like this. So if this is 1, 1, 1, this goes like this. So the function, the graph enters here, and then this is 1 over e. 1 over e is like 1 over 3, okay? And then from here on up to infinity, all this part is equal to this part, okay? All the way up to infinity is so close to x-axis that if you add up those things, well, actually you can add up those things and they will fill only this part. Okay, so this is going to be one of the examples that you should keep in mind, because we will compare. In a minute, we'll start comparison test. So you see, if I have another curve, which is like this, which is always under this, okay? Now I know that it has a finite area, okay? Because here a curve larger than that has a finite area. So if I am looking at an area like this, smaller than this, it's going to be finite. So it is a good practice to keep in mind some functions which have finite area in infinite strips. So this is going to be one of those major functions. So the second one, okay, so this is going to be a special case of a general type of integrals. So from 0 to 1, dx over square root of x. Okay, 1 over square root of x goes to infinity when you put x equals 0 here. So the graph is something like this. And here, if this is 1, this is 1, not to scale, okay? X, y. Okay, so what we do is we stay away from the bad point. So this point is 0, say r. Okay, we calculate this area and then send r to 0 from above to check if there is finite area under this curve. The function goes to infinity, but if it goes to infinity fast enough, there is no time to squeeze in infinitely many area there. Okay, so whatever that means. Okay, so let's do this. So the definition of this is limit as r goes to 0 from above. Okay, so r is larger than 0. Integral from r to 1 dx over square root of x. Okay, now I can handle this case. Okay, so let me erase this part. So this is 1. Okay, so I'm carrying limit operation 0 from above. So this thing, I know what this is 1 over 2 square root of x, right? I take the derivative, no, 2 times, right? Okay, so 2 times this. If I take the derivative of this, I'll get this. So from r to 1. Okay, so I evaluate this before I take the limit. Limit r goes to 0 of you put x equals 1, you have 2 minus 2 square root r. Okay, now that we managed to find an explicit expression, the expression is easy. I send r to 0 from above. Okay, you see in this expression, I cannot send r to 0 from below because r will be negative. So the direction of the limit is important, and this is equal to 2. Okay? So, believe it or not, there is exactly 2. Area of that is 2. So if you drove this one to a scale, so if this was 1, all of this area here up to infinity is another square of side 1. Okay, so I have, so I want to mention something, but I don't know if it is the right place to mention this. Okay, so let's do some more examples and see what's happening. So example 3 is integral from 1 to infinity dx over x. Okay, so you see there we had a function that goes to 0 as x goes to infinity, and there was finite area under it. So we suspect that maybe it will be the same here. So this is the integral. So this is 1. Okay, so this is the area that we are trying to understand. Okay, so the question is there finite area under this curve or not? Okay, so we do the theory, limit r goes to infinity, integral from 1 to r dx over x. So we just take an r here, we calculate this area. The function is continuous on this closed and bounded interval. So this is a proper integral. And in fact, we know exactly an antiderivative for this, which is ln x. Okay, so limit r goes to infinity, ln x. I'm not taking absolute value here because I know that x is larger than 1, so everything is positive. From 1 to r. Now I evaluate this part. This is equal to limit r goes to infinity, ln r minus ln 1, which is 0. Okay, so ln r, we know theoretically that ln r as r goes to infinity is infinite. So this limit is infinite. The limit does not exist. Okay, so we write there infinite, but that's just information. It tells us that this function becomes larger and larger without bound. Okay, so there's no limit for this. So interpretation of this is that there is infinite area under this, or since we don't know what it means, infinite area, we say that there's no finite area under this curve from 1 to infinity. But we can make it faster. This goes to 0 at a certain speed. Okay. Well, the speed. If I take square here, x squared, it will be a much smaller function like this. Okay. So maybe it will shave off some bad parts, and the area under that will be finite. So let us check that. Okay. So. Okay, so what about integral from 1 to infinity dx over x squared? Okay, so what's happening is this one. So here, okay, so let me exaggerate these things a little bit. This was y equals 1 over x. And we found out that the area under this is infinite. So we look at a new function, y equals 1 over x squared. So this goes to 0 faster than this. Maybe it will be so fast that it will cut off finite area under the curve. Okay, so we check if this is going to be the case. So limit r goes to infinite, integral from 1 to r dx over x squared. So this thing we can handle. Limit r goes to infinite, minus 1 over x from 1 to r. Okay, if I take the derivative of this, I get 1 over x squared. Okay, so this is limit r goes to infinite. So this is 1 minus 1 over r. Okay. Now I take the limit as r goes to infinite. This is 1. Okay, so it turns out that there is finite area, and in fact it's very small. The area under this is 1. Okay, so I know you can discover a theorem right now. If I have 1 over x cubed, okay, so 1 over x cubed, again at 1, this is the point 1. At the point 1, it will again start from here, but 1 over x cubed goes to 0 faster, so the graph of 1 over x cubed will be like this. All this shaded area is finite. Okay, so that's what we found. It is finite, and in fact it is equal to 1. Okay, so if I look at the area under the curve 1 over x cubed, 1 over x cubed, it goes like this. Okay, so I'm using only some part of an area which is equal to 1. So the area under the curve 1 over x cubed from 1 to infinity is strictly less than 1. I even know, I know it is finite, and I even know that it is less than 1. Okay, so this brings us to what we call the p-test. Okay, so in general, so let p be a constant, let p be a constant. Okay, so we look at the integral from 1 to infinity dx over x to the power p. If p is negative, then I'm integrating x to some power, some positive power, and you see that it goes like this. Even the function becomes unbounded. The interval is unbounded, so you don't have to take any integrals. You immediately know that the area under the curve is infinite, from 1 to infinite. So the problem becomes meaningful and interesting if the function goes to 0. Now, does it cut off finite area or not? Okay, so when p is positive, the curve 1 over x to the p cuts off finite area, and well, cuts off some area, is it finite or not? That's what we are looking. From what we did so far, if P is larger than 2, okay, here, if P is larger than 2, I know that it's going to have finite area, because if P is larger than 2, the graph of 1 over x to the P is going to be like this. So it is cutting off an area from already a finite area, so it will be finite. But if P is larger than 1, but less than 2, so somewhere in between, okay, then we don't know yet. So that's where we will find this. And of course, if P is less than 1, then again, we don't need this integral. If P is less than 1, the graph is like this. Okay, so it goes above this. This area is infinite, so if I'm looking at something larger, it's also infinite. Okay, so this analysis will only tell me about the curves in between here. Okay, so let's see what happens now. Limit r goes to infinite, integral 1 to r, dx over x to the p. So let us evaluate this. We can evaluate this limit r goes to infinity. So let me see if I did this here. So this is, why did I write it here like this? So let's see. Okay, so here let us say P is, when we are writing this, let us say P is different than 1, because here we know what P is. So here P is different than 1. So this is 1 over 1 minus P, 1 over x, 1 minus P. Okay? No, d P minus 1. So let me write it like this, x, 1 minus P, from 1 to r. Okay? So we take the derivative of this, 1 minus P cancels this. I subtract 1, I have x to the P, which is precisely this thing. Okay, let us evaluate this before the limit. R goes to infinite. So this is 1 over 1 minus P, R, 1 minus P, minus 1 over 1 minus P. Okay, now r goes to infinite. The only way this is going to be finite is this when this power is negative, 1 minus P. Okay, if 1 minus P is negative, then I have 1 over r to some power, and it goes to 0. If 1 minus P is positive, then this goes to infinite. Okay, so let's do this here. Okay, so this is equal to infinite if P is less than 1. In that case, 1 minus P is positive, so r to some positive power, and r goes to infinite, so that goes to infinite. And this goes to a finite number, 1 over P minus 1, okay, if P is larger than 1. When P is equal to 1, we already did this here, okay? So is infinite if P equals 1, we did this above. Okay, so this is called the P test. Okay, if P is less than 1, that is infinite, that we already knew. Okay, so that's for curves here. So let me draw that. Okay, so let's suppose we have these things. So if P is larger than 1, so I have these curves. These are y equals 1 over x to the P, P larger than 1, P less than 1. Okay, and then here I have these curves. This in between, these are, okay, y equals 1 over xp, P larger than 1. If P is larger than 2, we already knew this, but this also gives it in one stroke. And y equals 1 over x, it also has infinite area. That we can find here. You see the area is precisely equal to 1 over P minus 1. When P is larger than 1. if P becomes smaller and goes to 1, this area increases, okay? You get larger area, and eventually when this green curve touches this one, y equals 1 over x, you'll get infinite area. Okay, so this is called the P test, okay? This information, okay, so this is called the P test for improper integrals of the form dx over x to the p. Okay? We have time. So let's see what other. Just to confuse you, the situation is the other way around when we look at the area on this part. Okay, so you see these curves cross each other here, and their order is reversed here. Okay, so if this has finite area here, when it comes here, it has infinite area. Okay, and the same thing here. So this one, this red thing has infinite area here, but when it comes here, it is the smallest guy, and it has finite area. So let us check formally that that is the case. Okay. Okay, so we have time to do these things. So the main thing to keep in mind is this thing. Okay, so the other one, all you have to do is just remember that in between 0 and 1 things are reversed. And next semester you will use this one because you see we will try to add up integers. So let me just mention that in passing. Okay, so in passing, so next semester we will use this for infinite sums. Okay, so consider the curve like this. I start from 1. This time I'm not doing any scaling. So let's go like this. This is y equals 1 over x to the p. Okay, so let us suppose p is larger than 1. And then here we have, okay, so here 2. Okay, so this is 1 over 2. The area is 1 over 2, okay? And then here we have 3. The area is 1 over 3. Okay, so 4, 1 over 4, like this. Okay, so this sum, 1 over 2 plus 1 over 3 to the p, to the p, to the p. Okay, the curve is x to the p. 1 over 2 to the power p, 3 to the power p, 1 over n to the power p plus this infinite sum. It is positive. It is always increasing, and it is less than or equal to integral from 1 to infinity dx over x to the power p. Okay, and we know precisely what this is. This number is 1 over p minus 1. Okay, now we have numbers, positive numbers, increasing, but they don't go to infinity, so they must converge. So we did this with limits. So these things add up to a number when p is larger than 1. Okay, so if you reverse this, if p is less than 1, okay, so next semester you'll do also divergence. If you start adding up from here, you see that now these sums are larger than this area. Okay, if p is less than 1, the area under the curve is infinite, so these sums will be infinite. Okay, so that's how you will use this next semester. Then once you know when these things converge and diverge, you use these to find the divergence and convergence of other things. Okay, this is the only method to understand if these things converge or diverge. Okay, so that's what you will do. That's where this thing will be useful next semester. And then, of course, once you understand how this trick works, instead of using this function, now you can use other functions and you can add other numbers. And you can also tell if they are convergent or divergent once you can settle the problem with the improper integrals. Okay, now let's pass to the improper integral between 0 and 1. Okay, so let's see. So this is 6, I think. Not to confuse ourselves, I'll say let Q be a constant. Okay. So we want to understand 0 to 1, dx to the power x to the q. Okay, so the picture is again the same. So this function goes to infinite. So this is 1. What we do is we stop at r and calculate this area. This is y equals 1 over x to the power q. Q is positive. Okay. If q is negative, then you are looking at y equals x to some power, positive power. It doesn't go to infinite. It's a proper integral. Okay, so we are not interested in that. So this is limit r goes to 0 from the right, integral from r to 1, dx x q. Okay. So again, let us assume that x is different than 1. Or rather, q is different than 1. Okay. Then this is limit r goes to 0 from the right. So let me just write x minus q plus 1 over minus q plus 1 from r to 1. Okay. So we evaluate this limit. R goes to 0. 1 minus r minus q plus 1 over, I'm just copying this from here because we don't have time for this. Okay. So you see that this is 1 over 1 minus q if q is less than 1, and infinite if q is larger than or equal to 1. Okay, so but let me write larger than 1 because we didn't do the equal 1 case. Okay, so if q is less than 1, then here this is r to some positive power. When r goes to 0, it goes to 0, and you get this. If q is larger than 1, then this is r to a negative power. So this is of the form 1 over r. When r goes to 0, it goes to infinite. Okay, so here what happens when we have q equals 1. So you are integrating 1 over x. It is ln x. Okay, so this is limit r goes to 0 from the right of ln x. Okay, absolute value of x from r to 1. Okay. Now we evaluate this inside the parentheses. ln 1 is 0, so we get limit r goes to 0 from the right minus ln r. As r goes to 0 from the right, ln r goes to minus infinite. I have minus in front, so this is infinite. Okay. So you see that this is reverse of the previous situation. But sometimes it is confusing. If we also call this p-test, it is sometimes confusing. But basically, we'll use p-test for things like this. So it is enough to remember p-test for these things. And if it is between 0 and 1, just remember that it's the other way around. Okay, so let's do one more example and then stop. So let me do just this example. Now we said the interesting thing is when the function goes to 0. Okay, so the interesting is to draw a picture and check if the area is finite or not. So our last example is y equals ln x. So y equals ln x, where x is between 0 and 1. Okay, so we can take 1 here. So the graph is something like this. Okay, so this is y, this is 1, this is x. ln 1 is 0, so it goes like this. Okay, so we are trying to check if there is finite area or not. So what we do is we choose R here. We calculate this area. Certainly that area is finite. And then we take the limit as R goes to 0 from the right. Okay, so we are interested in from 0 to 1 ln x dx. Okay, so this is the improper part. So limit R goes to 0 from the right, from R to 1 ln x dx. Okay, so we know what this antiderivative is. Limit R goes to 0. For these simple things, you can do this by trial and error. If I multiply this thing by x, whatever I see here, if I multiply it by x, then I take the derivative of this. The first term I'm going to obtain is this. Okay, but then I'll obtain some other terms. I play this game. If the function is nice, it stops somewhere. Okay, so that's how you find antiderivatives for simple functions. So I look ln x. Okay, if I take the derivative of this first, this derivative of this times this, I already get this. Next, this times the derivative of this, which is 1 over x times x. So the derivative of this will give me this plus 1. Okay, now I have to get rid of 1, so I subtract x. Okay, now I take the derivative of this, you get this. So this is from R to 1. Okay, so let's evaluate this. Limit R goes to 0 from the right. When you put x equals 1, ln 1 is 0, you get minus 1. Then minus R ln R plus R. Okay, so you want to take the limit of this. Okay, now limit as R goes to 0 of R times ln R. We did these things. When a polynomial and logarithm fights, the polynomial wins. So this goes to 0. This goes to 0, so we get minus 1. So how can an area be minus 1? It's either you made a mistake or the area is under the x-axis. Okay, so here you see the area is under x-axis. So the area is equal to 1. Okay, all that area from 1 to 0. Okay, so this thing goes to infinity. But if you consider this box here, all the area here fills up this part. Okay, so that is okay, so these are the first examples. So on Friday, we'll start making these comparisons formal. Okay, so on Friday, we'll do comparison tests and other things about improper integrals. Okay, thank you.